There we go. All right. Thank you everyone for joining us on this week's AME seminar. It is my pleasure to introduce Ander Biguri. He's a research associate at the University of Cambridge, and he'll be talking about the mathematics of inverse problems in machine learning for CT reconstruction. Thank you, Ander. Take it away.
Thanks a lot. Well, thanks everyone for coming, and thanks Jorge again for the invitation. It's nice sometimes to do a little bit of like preaching of the research that we do, so that's really nice. So as you said, I'm going to talk about computer tomography, which is what I've been mostly doing for the last almost 10 years, and nowadays how we do machine learning and like introduce a little bit of like software and so on that we're building around it here in Cambridge. So briefly, I'll tell who I am because Jorge has just to do a little biography, and then I'll kind of like first try to make the case of why tomographic reconstruction is a thing that we should be thinking about, at least to some degree. Very often people working in biomedical engineering to some degree assume that the machine just gives you CT image, and that's good, but that process is self-complicated, and we can do better in many ways. And I'll talk a little bit about how this is done typically with like non-machine learning mathematics, just with iterative reconstruction, and then we'll kind of like jumping into the machine learning part of this and kind of like how we mix the mathematics and the machine learning. So very briefly, I'm an engineer, not a mathematician, even if now I work in a math department. And I specialize in image processing when I was doing my engineering degree in Spain. And then I moved to do my PhD in the University of Bath in computer tomography, particularly for lung radiation therapy, and particularly for the case, with this like proton therapy and this kind of like targeted radiation therapy, novel targeted radiation therapy installations. We're thinking how to do imaging in 4D, right? And particularly in motion, correcting for the motion without increasing a huge amount of the X-ray dose. So that's what I get a lot into I got a lot into the reconstruction and to mathematics and to GPU computing and medical applications, right? I did it a couple of years of a postdoc, and I did it in the University of Southampton here in the UK. Also in tomography, particularly they have like a very big tomography lab for scientific applications. We'll show you some images later on. So we can see here a coffee bean that I'll show you a little bit better. So this is kind of tomography again, but you don't care if the patient dies because there is no patient. Basically, it's just like stuff that you put in the scanner. So the challenges tend to be different. Either it's computational size and I did another a couple of year postdoc during the pandemic at UCL with General Electric Healthcare, where we were looking at positron emission tomography and particularly, again, motion again, how involuntary motion impacts scanning and how to correct it and so on. But finally, nowadays, I am in the University of Cambridge. So I am in the group of in the Department of Applied Mathematics and Theoretical Physics. So I work with a bunch of mathematicians, and particularly in the group of Professor Carola Shonleaf. And it's a very big group, as you can see. I'm not even in this photo. This is, more people than this in the group. There is a big list that probably is outdated by now. In what we all work in imaging in general through the mathematical lens, right? So a lot of us are doing kind of like machine learning. I do more applied machine learning, but some people are trying to build mathematical foundations of machine learning, but also PDs on images for painting or variational methods, image parcels, anything that has to do with imaging and mathematics is the kind of things that our group does, right? So we obviously have a huge amount of collaborations around the university because we're kind of like a math center, but a lot of other people around us are kind of like the application people, right? So we have a lot of like synergies around the university and the world, I would say. So that's my brief biography. Now I'm, as I said, a research associate here. And that I'll introduce you now the kind of stuff that I do. So you all probably know computed tomography, is this machine, this is like Siemens one, that it goes around the patient and, gets this sinogram, measures this sinogram, which is, depends on the angle and the angle acquisition. It produces these less weird things. And the process of tomography reconstruction is coming from this sinogram to an image that the doctor, the clinician, or the scientist can actually read, right? And that's what I'm going to be talking about, basically, the process from coming from this sinogram to the image. I may touch a little bit, but mostly not going to touch what we do with the images afterwards, right? Like the goal is to make this process better, right? And most of the examples I will be talking to, not in machine learning side, will actually be of cone beam CT. So your standard fan beam CT is the most used one for diagnosis, but cone beam CT is mostly used for treatment and dental, and all the industrial machines are cone beam CT and so on, right? Ultimately, the difference is computationally more challenging to do cone beam CT because you cannot separate the problem in slices. But also it tends to be used in applications where the radiation dose, you want repeated scanning and so on. So the dose is much lower and the image quality is worse and so on, right? So just kind of disclaimer that most of what you are going to see CT all the time, but a lot of it will be cone beam CT. Just as I kind of like briefly said before, you probably want to introduce much more like what is used in medicine, because you probably just like by general knowledge know, but actually it's also used in industry, right? And science. So these are images that are from the lab when I was working in Southampton, just a random set of examples. And you can see, for example, I really like this one of the dinosaur. This is a pliosaur fossil that they found, and you can see a human skull here. So the CT scanner that they have could walk in. I think they scanned the piano once inside. So it's a big CT scanner, right? So like it's not just everything I will be probably focusing will be in medicine, but there is a lot of like use of these machines somewhere else in science. And in fact, they're more and more being used, right? Because they're becoming cheaper and people are starting to understand them more. But you can see also for engineering and, kind of like histopathology, but digital histopathology and, some other things. Anyway, so what is the problem? Why is reconstruction a problem? The problem is because I simulated here someone's head, and this is the measurement that you would get, right? And this is basically, this sinogram corresponds to this head, right? Instead, I added a tiny bit of noise to that sinogram. I didn't make a mistake. These are two different sinograms, and even if they look the same, and this is the image that it would actually reconstruct if you actually use this sinogram. So CT reconstruction is an extremely ill-posed problem. Mathematicals call it an inverse problem. It's an extremely ill-posed problem. And ultimately, it's a problem where like a tiny amount of noise or uncertainty in your measurement can completely destroy your reconstruction if you use your standard algorithm. It's like your standard. This is using the standard medical algorithm that you use in the clinic, and therefore, but almost intuitively, we know that reducing the dose, like noise is related to dose. So the lower dose that you give, then the higher noise that you will have, and reducing the dose is exactly what we want, right? Like if you want to do a screening of patients, or you want to do, nowadays image-guided therapies, either radiotherapy or surgery and other type of like medical interventions are more and more common. And basically that that to try to do those without damaging the patient with too much X-rays, we need to lower the dose, and lowering the dose ultimately means that because physics, we will have this level of noise, right? So kind of like to summarize, the rest of the talk will be, okay, so what can we do about this? So briefly, the general algorithm that is used everywhere, and don't worry about the maths, I don't want you to keep track of them. But the general algorithm that is used in most clinics, even if nowadays they're updating, is the filter back projection. And it's basically an analytical the approximation of the analytical solution of the tomography problem. Okay, so it doesn't really matter too much. You do a filtering and then something called a back projection, and you get a reconstruction, right? And it's basically what is used everywhere, and it works really well as long as there is no noise or the noise is not very high, right? So if this is a simulation I did in the sinogram, the moment you go lowering and lowering the dose, the algorithm kind of like significantly starts failing, right? And I would also like to point out that clinical dose is not a safe amount of dose. A clinical dose is the dose in where we can still see something when the algorithm fails, right? Like this dose has mostly been driven and chosen such that we can actually see something with this algorithm rather than because it's safe for a patient, right? So kind of like the big goal, therefore, of like a lot of the research in iterative reconstruction is to find better mathematical methods rather than this filter back projection to be able to get as close to the no-noise image using 10% or even 1% of the clinical dose, right? And again, this could empower a huge amount of future clinical applications, such as one of the most obvious ones is screening, right? You could screen patients every year for lung cancer and catch it really early. And that I think there was a study done in the UK that said that like the mortality would reduce by 50% or something like that, right? So it's a significant health benefit. So briefly, mathematically speaking, what we do, and like just bear with me for a little bit, is that we're interested in a solution of this linear system of equations, ax equals e plus equals b, in what we're going to call x our image and b our measurement, the sinogram. Okay, and a is something that basically transforms from this image to the sinogram. So in practice, what happens is that in this image here in the corner is that every X-ray, we can simulate every X-ray as like an integral over a volume, and every column, every row of A will be basically intersections of this X-ray with the boxes, right? So we can actually construct this A once we know the geometry of the scanner, and then we'll have X, and then X's are unknown, E is some noise, and B is the sinogram. And we do this kind of linearization of the system of the problem because obviously we know how to. Mathematics is full of algorithms that can solve linear system of equations, right? And therefore we can propose a minimization function when we go, well, there is some distance function between my image and my sinogram, and then some other new information that I know about the nature of the image, which is called regularization. And generally, we use this one with the 2-norm, right? So we say, well, I want to minimize the distance between my simulated my image simulated with my scanner geometry and what I measured, and then some regularization. So this is kind of like how traditionally mathematically we've been formulating this problem, right? In what they're often called iterative methods. They're often called model-based methods, but mathematically we like to call them the variational formulation of the problem, right? The variational regularization. So briefly, a lot of my career has been working on these methods until I came to Cambridge. So most of it, I wasn't working in machine learning, and I wasn't working in machine learning, and I was doing a lot of research, but I was building the Tigre toolbox all along the way. And Tigre is basically a MATLAB or Python toolbox that basically gives you, it's super easy to use. If you have data, you can in 2 lines of code, you can do reconstructions. It supports 8, I think, clinical and industrial scanners, and is super fast also, which is quite important. And Tigre is basically a tool where me and a relatively big community of people have been putting all the mathematics and all the methods that we've been, doing for tomography reconstruction over the years, right? So if you're working on this, I think I would say it's worth having a look. The entire point is that you don't need to know any of the maths that I told you about to get reconstructions. So that's kind of like big idea of Tigre, but also that if you know about the maths and you want to add your methods, it becomes really, really easy. It's very kind of like vanilla Python, and you just replace a couple of lines of code and you can get extremely, fast reconstruction tested in hundreds of data sets by now. So Tigre, in fact, has all of these different mathematical algorithms because ultimately some algorithms are faster or some of them are are slower but will get you a better image, or some of them are better when you have high noise. So for example, this is a simulated study but of lung convexity when like FDK is your clinical, what you like. If you had like a Siemens machine, you could get this image, and just by changing the mathematics and for higher computational cost, but actually still within a minute of computation, you can get a much better image than your clinical one. And in fact, if you use a more sophisticated mathematical method, you can get a much clearer image, right? And particularly in this case, these are images to treat this tumor that we have in the lung, and this one is much closer to the original one and it's much clearer for the machine, right? So they can have an impact, right? And this is not even with a lower dose. This is actually what you could get from the machine. So we could actually do much better by reducing the dose with this algorithm. Right? So this is just kind of like to show you that these mathematics actually work and we've been using it, and this is really important to use them, right? I'll show you a couple of images more. This is a coffee bean. So if you've never worked with kind of like this kind of scanners, you can get very big images. So this volume is 3,000 by 1,000, and every pixel is about 4 microns, so quite small. And we took a huge amount of projection. In fact, it took 45 hours to scan. And with Tigre, we could reconstruct it in 4 hours, which is a lot of time, but actually, you can imagine this data set is really big. Yeah, even your standard reconstruction will take about half an hour. But one of the important things is that even in these very, very, very high, very controlled environments in where like the amount of radiation that you can put to the sample is basically irrelevant, you can radiate it for as long as you want. We can show that using iterative algorithms rather than your standard reconstruction does produce much cleaner images, right? Particularly, this is like a proxy to study porosity of materials, and you can differentiate what's a real hole and what is an artifact of the algorithm much better in the iterative algorithms, right? So, and then this is just another example of a synchrotron data set, but ultimately this is what they were seeing. And if we use a different bunch of algorithms, and this is just also to show that they behave differently, you can essentially go from not seeing almost anything to actually seeing very good images, right? So all of this just to make the case, hey, this is important, we should care about this. So can we do better using machine learning? Yes, is the answer, as I put that in small, and I'll clarify. So it's very vague what it is to do this with machine learning, and as you can imagine, with the boom of machine learning, there are many, many methods to do it. So I'm going to very briefly explain the 4 main categories of methods that exist to how we do this with machine learning, right? And this is a core research, my core research topic right now, and also a big part of my group, right? So we all play, work with a lot of these methods. But I'll briefly explain what these are. Yeah, so you have an idea of where the field stands right now. So the obvious first way to do anything with machine learning is to denoise an image, right? To do an image-to-image post-processing thing algorithm. So you reconstruct it with your bad algorithm, and you make a machine learning that learns how to denoise the image, right? To clean the image. And this is kind of like if you do any machine learning, this is the most standard way. You kind of like your first tutorial on machine learning will teach you how to do something similar to this. And this is one of the examples, and this is clinical, and this is your iterative reconstructions, the one I've been talking about, and this is your machine learning model, and you can see that they perform quite similarly, and actually this one, the machine learning one, does a little bit better, right? So not much mystery. You throw it a bad image, and you throw it a good image, and you say, hey, clean this thing in a supervised way. And this works well. The only thing that we as mathematicians worry is that when we have the other methods, the iterative reconstruction methods, we constantly are comparing our image estimates with our measurement, and we make sure that there are no hallucinations and things like that. And what we can see in these kind of methods in practice is that sometimes there are hallucinations. Because you reconstruct the image and then you give it to a black box to do something with it, right? And it's not, it's not very nice that we don't know what we're doing with medical images, right? Like if it's a photo of a cat, it doesn't matter. But if it accidentally deletes like some important feature and we don't understand, that's not super nice, right? So mathematicians then have been kind of like try to take iterative reconstruction methods, which is the one that I've been talking about before, and the word integrate, and mixing them with machine learning, right? And the way you do this is, I'll give you like a brief example, but it's fairly easy, right? So you have your gradient algorithm. This is your standard gradient descent, and you have here before I call it X, well, yes, for the change of notation, but this is your image estimation, and this is your sinogram. You say, okay, my gradient descent will be, I update my gradient, my image with the gradient, right? And this, you could do this, and this is an iterative reconstruction. And one of the things you can do instead is to say, well, instead of adding my previous estimate to the gradient, I'm going to introduce a small machine learning model, just like a tiny one. Tends to be like 4 convolutional layers or something like that. And I'm going to just give it as an input my previous estimate and my gradient, and then see what it does, right? You train it, and what tends to happen is that you tend to be able to build, so this is essentially, right? Like you have an image, you have the gradient, and then you put a little machine learning, and then you keep doing it. You need to put a different machine learning in every step, and therefore you need to unroll the method. You need to define how many iterations you're going to do from the start. A training basically, but what tends to happen then is that you end up getting very small networks, because these little models are very, very small compared to a unit. And because you're using all this information that you know about the geometry, which is this matrix A, you're simulating your image, you're comparing to your data, tends to happen as this reduce hallucinations quite a lot, but also increases performance quite a lot, because it doesn't need to learn what city is. You're giving that information to the model, right? And also they're not, some people say they're interpretable. I would say they're not, because once you add this thing, you don't really know what it's doing still, but you're like, it's closer to something that we understand, if that makes sense. So the kind of like, the way this tends to be done in the literature is, and this is one of the most famous ones, or learn primal dual, is that you take your mathematical description of an algorithm, and then you go like, well, you find something that is like, can be replaced by machine learning. So in this case, this like something called this proximal operator, which is a little step on a direction, and you replace it with machine learning model, right? And so the most famous one on this field is called learn primal dual, and got this thing where like you have models all in the sinograms and in the image, and you go back and forth and whatever, but it basically performs really, really, really well. In fact, it's an algorithm from 2017 in the machine learning world. This is really, really old, and it still is one of the best performing ones very often, right? So this has a lot of power. Just some examples in what it works, and particularly these last two, this learn primal. So another one is the learning and regularization. And this starts moving a little bit more in the math side, so I'm not going to explain a lot. But in the beginning, I basically told you that you generally have a minimization problem, and you have this first part that tells, oh, how close is my current image estimate to the what I measured. And then there is this other part that is what we call regularization, which is imposing some knowledge about our images, right? So for example, a very common one in the traditional method is, well, I know pixels one next to each other should have the same value, right? So if I add all the differences between pixels next to each other, that's total variation, and lower total variation, meaning pixels next to each other having the same value, is more natural than not, right? So we'll promote these kind of solutions of the possible solution. So one idea that was actually developed in the sorry, there is a question. So yeah. So in the previous one, in the learn iteratives, in the iterative and raw ones, they are trained all at once. So training is much computationally slower. Actually, you don't train every step. You train then the entire unroll iterations, basically.
Thank you so much.
Yeah. So for going back to learn regularization, then the idea then of this mathematically, the idea of this regularization, also often called a prior, is if you do statistics, it's a function that will give us a small number if the image looks appropriate and a large number that if the image is not appropriate, right? So what we can do then is say, well, I'm going to build a neural network. I'm going to give it unpaired good and bad samples of what an image looks like, right? So it doesn't even need to be of the same sample or patient. As long as you have enough examples of good and bad, and you're saying, I want you to learn a distance function between these two distributions, right? So I want whenever you see a good guy to give me a small number, and when you see a bad guy, to give me a high number, right? So the good thing is that you can train this like without actually any real data. You can simulate even like the levels of like bad bad images. You can choose what kind of thing you consider bad. Could be a lot of noise or artifacts of different types if you metal artifacts or other things, right? And then you gain this function that is a function that is differentiable that will give you a low or high number, right? So the good thing then is that we can just take this thing and plug it in the iterative methods. Because most of the iterative methods that I was talking before, they have some mathematical constraints of what this regularization can be, but it has to be differentiable and continuous, right? And a neural network is by definition, so or by construction. And in fact, we can actually do more things because we can constrain this neural network in certain ways, in where we still have all the mathematical guarantees of the original algorithms, right? And this is it sounds silly if you're like maybe a biomedical engineer, but as a mathematician, working with mathematicians, it's kind of important to have this like knowledge that the algorithm that we give you will always work, right? It's not going to do something crazy. It's not going to give you a very bad solution, right? So these are very powerful because you can train them separately. Training them is very fast. You don't need pair instances of good and bad image, high dose and low dose images, which inherently will never have in computed tomography, right? Because it's unlikely that any ethics committee will approve getting two scans of the same patient at different X-ray doses. And then you can deploy them really easily, right? Because you already have your algorithm and you just replace one line of code by a neural network and it does the job, right? So they're quite powerful and quite liked in the mathematical community, if that makes sense. So, okay, but this is kind of like the maths of how they work, don't worry. And this is an example, right? So before we're talking about Len primal dual, for example, and Len primal dual seems to outperform this kind of methods because ultimately it has more learning power, can do more to the image. However, this AR and ACR are this kind of learn regularization, and they're not amazing. They are certainly better than standard reconstruction, not as good as Len primal dual, but I'm safe by telling a doctor you can trust this image, right? Like I know it's doing the right thing. And in fact, we're still working a lot in these methods to like improve the performance without losing the mathematical tools, the mathematical guarantees that they come with, right? This is quite an ongoing research topic. Finally, I'll talk about plug and play, which is a concept that also doesn't necessarily come from machine learning. And it's, again, don't worry about the math. The only thing that you need to know is that to solve this equation above here, there are some algorithms like ADMM and FISTA and other things that, they're like, to update the image, you need to do 3 steps. And interestingly, often this one step in the middle is the same as a denoiser, as denoising an image. Right? Like mathematically, it is exactly the same equation as you would do if you were denoising an image, right? So what you can do then, and this is where the name comes from, is you can train a denoiser. So again, you don't need raw sinograms, which is really hard to get, to do the training of all these models and so on. You can just even simulate the noise yourself, right? And at different levels and so on. And you can train a neural network to be a denoiser, right? Separately. And then when your actual sinogram data comes in, what you do is you replace that step of your algorithm by the neural network that denoises, right? And again, we can prove a lot of mathematical things about this model, and they also work really well, right? Because you're not breaking the math yet using all the power of machine learning. That makes sense. So this is one of the examples, and I would say that this is from this paper. I could say they didn't push it really hard, but in any case, you can see that if you take the algorithm without the machine learning step and then with the machine learning step, it just like removes the noise quite a lot. In this case, perhaps the difference is not enormous, but in our test that we've done ourselves, we can see that they can do much better in cases where the standard iterative reconstruction will not perform. So finally, I'm going to briefly say that there are a growing set of self and unsupervised methods. So methods that don't require clean data, which I think for tomography are very important, right? Because it's likely that we'll never have it, basically, right? Either a clean reconstruction or a very high quality sinogram, right? So there are quite a lot. One of them, they're often very smart. One of them is equivariant learning, for example, which is the idea that you don't know what the ground truth is, but you know that if you rotate the image, you move the sinogram and pretend that it was acquired like 90 degrees with a 90-degree shift, the image that you're getting should still be the same, right? So you can, learning, do 2 levels of 2 gradients, and then in the loss, just say, well, if I rotate one of them and then unrotate it, you should get the same, right? And this actually is incredible because it performs almost to the same level as supervised learning, right? And there are few kind of like other really smart models out there to do this. So I guess one of the questions is, very good, you went through a lot of math and so on. So can we use this, and how can we use this in the clinic, right? Because I saw some examples of iterative reconstruction, in the beginning without machine learning. With like this is already kind of like Siemens and GE are adding them into the machines. It's something that we can use. We know it works. Overwhelmingly tested in the literature that these are better, and even the industry is starting to move that ways. But the machine learning is fairly new and is not that much. So I would say, no, we cannot use them yet. And hopefully we can fix that, right? So it's still not at a stage where we can really use it, I would say. With clinical data, I wouldn't be very happy if someone would come and say, hey, let's use your model, because I would be a little bit too many unknowns. And part of the challenges is that this is kind of like a small sub-niche of machine learning, and there is quite a lack of comparability and reproducibility. All the papers do a different geometry and a different level of noise and different data sets, and there is not like big challenge or anything that people are doing out there, right? Like you see the papers and you see the same models perform differently different papers, right? So it's really hard to, like, if someone comes to me and say, like, which one should I use? I would say, I don't know. We just don't know which one is the right one. And we haven't really tested them a lot. Like mathematicians are developing a lot of this, and very often they test them in like tiny sample images, and we don't really understand when they fail, right? Like when can you use some? Like, as we can see in the iterative reconstruction, the reality is that probably some of these methods will be better in certain cases and some others will be better in others. And we don't know, basically, right? We don't really know how to evaluate them very well. They're almost never been tested with real data and almost never used in 3D, which is where they're most needed, because with fan-bin CT, we nowadays can get fairly good images, but in cone-bin CT, that's where the real, real point of change that can be for the medical community, and these models are computationally too expensive to do in 3D. And the field is barely new. I mean, every year new methods that do a significant change are still coming. So there is also like a lot of fundamental research that is missing there. So I'll show you a little bit, a few things that we've been playing with to tackle some of these things, right? So this very briefly, I'll kind of like summarize a few papers in one slide, right? So one of them is actually benchmarking them, right? So we need the answer of when do they work, right? So there was this student, Max Keys, who spent about 12 months of his PhD scanning in a lab these samples, and he scanned all of them in high dose, low dose, with filtering, without filtering, and many different ways. So we suddenly is the first data set that we have with real data in where we can actually have actually samples of like what it is, good and bad. Obviously, it's not patients, right? It's just we couldn't do it otherwise, but it's actual real data. We make actual assessments with it, right? So basically, we did a benchmarking paper where we compared 12 different machine learning methods of all these categories that I explained before in 9 different cases. So it's full data, limited angle, sparse angle, so just taking less, right? Just lower dose of the source, and just when you have less filtering. The results are overwhelming, so don't worry. But what we ultimately see is that obviously some of them do better in some cases, some in others, right? This is just a simple example. Your clinical case, and in some cases, that's terribly bad, and then a post-processing algorithm and iterative control algorithm, right? And how we can, what is more or less the performance improvement that we're expecting, and so on, right? This concept. So that's one of them. It's the first time that these things have been compared. Definitely first time that have been used with real data. So at least a step in the right direction, I think. We've also been actually thinking a lot of what it means to have a good result, because this is an example that when I was working with the LADC data set, and you have tumors, right? And you can see the image quality number, like SSIM, which is a very common image quality number that we get here on average for all the samples, right? Now, we definitely saw that INNET is the best one. Again, it's an unrolled iterative net, so it doesn't really matter. It's one particular model, right? However, I don't think it's the best one because for particularly small tumors, it produces a very blurred plots, and it adds a lot of like weird things in the lines that are not there. While, for example, this one that is a post-processing method or Lempremal dual actually do a much better job of like highlighting the tumor, right? And in fact, we have a couple of papers. Well, I mean, one of them, it's this first one, but I think this bottom one, but it's worth reading. Both of them by Anna Breger, who's a postdoc in our group, in where we saw in one of the papers 8 different medical examples in where this metric is, does not select the best image by a doctor. And then the other one, just Anna studies actually better metrics to look at, right? So part of the problem is that what the machine learning community accepts as the best results may not be the best result, right? And in fact, there is another thing, which is a postdoc that was here for a bit and now is in Sweden, Milen Balat and some of us have been working, which is this idea of task adaptation, right? You don't want to make the best city image. You want to make the city image that aligns best with the task at hand, right? And it could be detection, or it could be quantitative values of the tumor, or it could be various things, right? But almost always when you're doing imaging with CT and other medical devices, the quality of the image is not the end goal, right? You want to use that image for something else. So there are ways to train the models for that, to do the best image for that task rather than just the best image, right? And this, I think, a very powerful idea that we're exploring much more in different applications. We did a challenge this year in ICAS for reconstructing 3D data. We have a preprint out there, and the data is out there. So hopefully this will encourage more people to play with 3D tomography and to make models that are computationally feasible. It was really good because NVIDIA won the second prize, and we got super high quality submissions. So it's kind of another push into the right direction, hopefully. And the final push, which is kind of perhaps the title of this work, of this presentation, is the Lion toolbox, right? So one of the things that we definitely notice, and I would say is very common in machine learning, is that reproducing other people's code is a pain. It's really hard. And when you are working with models that require forward operators and things for tomography and a lot of other moving pieces, all of the code you have there is completely disastrous. And I include mine. I'm not trying to tell other people off. I include mine. It is hard to reproduce paper, and when I joined my group, there were 7 people working in these kind of methods to some degree, and they all had their own implementations, and none of that was shared because it didn't work in different computers, and that they could not give me code that reproduced the papers they have already published, right? Machine learning reproducibility, and it's not an issue only in tomography, but I think it makes tomography worse. And particularly important also that all these great mathematicians working in tomography, in applications for tomography in these algorithms, have no idea of tomography, right? And this is not their fault. It's fine to be a fantastic mathematician or optimization, but it often means that the examples they put in the papers are not the best, right? But also, if you're working in the other side and you're biomedical engineer, maybe half of the talk that I already gave you were it was too mathematical for you and you understood nothing, right? And that's bad, right? Because these methods can do a lot, and the fact that they're really hard to explain and to code for someone that is in the other side is not ideal, and it will not move the bar, right? It will not progress the field. So the same way as I did with Tigre or Tiger, I'm now doing it with the machine learning side, which is with Lion, right? So trying to make a toolbox, a city toolbox, a machine learning toolbox is built on PyTorch to make city accessible for machine learning researchers and to make machine learning accessible to city researchers, right? And everything that I mentioned so far is there, all the benchmarking, all the data sets. The software has data sets that will automatically be downloaded for you and put somewhere in your machine, and it will load them in appropriate way. It has all these machine learning models. We're building a lot of evaluation metrics that are not just your standard. Just general tools like simulating noise in city is not trivial, and it's not just adding some Gaussian noise to your image. That's not how city noise looks like, right? And so have tools that do that for you. And if you don't want to know how that works, that doesn't matter because we'll do it for you. And we can all use the same noise simulations. We have codes that will train machine learning for you, the solvers that will do unsupervised learning or supervised learning or whatever you want. It will keep track of everything or whatever for you. And particularly the last one, which is something that admittedly, Lion is still not out there. We just released 0.1, so it's really work in progress, but it's for reproducibility, right? So we want to make sure we're writing a data format in such way that the models will be saved in a way that you can open them 10 years from now, exactly how they were saved, in which commit of your Git repository save them. You can, from the code, just build all the data sets and models and evaluation that save that model without having the original script, right? Like a lot of this is about making sure that the models we train, we're not born in the planet training the same model thousands of times just because we don't know what variable someone used in this PyTorch script, right? So Lion wants you, if you work on this and you know anyone working on this, in any level of the computer tomography, either very machine learning or very applied tomography, we want collaborators and people to add their code because this is something for the community and that requires the community to be in. So do join if this is something interested for you because like anything will go in. Basically, right now at this stage, we're building this big platform, and it requires, we're adding a lot of ourselves. We're like at least 12 people in a group that we're like to some degree adding things, but anyone is welcome to come and add things, right? So we want you to use it, to break it, to reuse the model for your research. It's free, just use it, but also to develop it, with models, methods, data, solvers, anything. Anything is welcome. So some final thoughts. Ultimately, the entire, my entire research and this entire talk can be summarized that better reconstruction can have a significant impact, and it has had significant impact in medicine and many other applications. So actually, it's part of the pipeline that is important, and that we're building Lion, which is a work in progress, and hopefully this will help everyone. And if you want to be involved, send me an email. You have the library there, the toolbox there in this GitHub link. And I think that's it from me. If you have any questions, now's the time to ask.
Go ahead and thank Ander for a great, very interesting talk. Thank you, Ander. If you have any questions, feel free to unmute or type it in the chat.